Hi there, and welcome to my video on IPv4 addresses and class-based network systems. Before we get started, it is important to note that class-based addressing was deprecated decades ago, and modern networking is based on classless interdomain routing, or CIDR. However, many academic institutions still teach the class-based system, and it does give a simple demonstration of how address masking works. What you see here is a simple IP address. You would most commonly see them represented in dotted decimal notation like this. However, they can also be represented as 4 individual numbers between 0 and 255. This can be further represented as 4 bytes or octets of 8 bits each. This representation can make understanding address masking easier, which we will get to a little later. The first thing to know about class-based networking is that all possible IP addresses are split into 5 classes. Each of these covers a range of IP addresses. However, it is easier to demonstrate how the classes are defined by looking at them in their bit form. Classes are identified by where the first 0 in the address is. Class A addresses have a 0 in the first bit space. Class B addresses have a 0 in the second bit space. Class C addresses have a 0 in the third bit space, Class D addresses have a 0 in the fourth bit space, and Class E addresses have a 0 in the fifth bit space. The classes determine how the addresses are split up into subsequent components. Class A networks use 1 byte to address the network and have 3 usable bytes for subnets and hosts. Class B networks have 2 bytes to address the network and 2 usable bytes for subnets and hosts. Class 3 networks use 3 bytes to address the network and 1 usable byte for subnets and hosts. Class D networks are reserved for multicasting, and Class E networks are reserved for future use and research and development. Let's take our sample IP address from earlier and work out which class it belongs to. As the first 0 is in the first bit space, this is a Class A network. Because of this, we know that 1 byte is used to address the network, and 3 bytes are available to address subnets and hosts. The next aspect we will look at is the network mask. The network mask is used to find the network address from a given host's IP address. For a Class A network, this network mask is the one shown, but can be better identified with its dotted decimal notation of 255.0.0.0. To get the network address, we need to perform a logical AND operation on the given host address and the network mask. This will then give us the following network address. A logical AND operation basically results in a 1 where both the address and network mask had a 1 and leaves us with a 0 for every other bit. We can now start to list some of the information we know about this network. So far, we have the given host address. We have a given network mask based off the class of network. And finally, we have a network address calculated from the host address and network mask. However, this will still be broken down further into subnets, so let's investigate that. As we've already mentioned, with a Class A network, the first byte is used to address the network, and the remaining 3 bytes are used for subnet and host addressing. To make things easier, we can take the 3 groups of 8 bits and read it as one large group of 24 bits. These bits can then be used to subdivide the network into the number of subnets we require. We can really choose any number of bits to address the subnet, and then the remaining bits are used to address hosts. As you can see, the more bits we use for the subnet address, the less we have to address hosts within that subnet. What we're after is a good balance of the number of subnets we can have and the number of hosts we can have per subnet. Taking our example again, let's work out how many bits we want to address the subnets and how many we want available for hosts within each subnet. We will assume that we have 1,200 subnets that we want to include in our network. To work out how many bits we need to address these subnets, we convert 1,200 into binary. As you can see, this binary number is 11 bits long. Therefore, we need 11 bits for our subnets. So now we've split our 24 bits up further. We have 11 bits used for the subnet and 13 bits used for the individual hosts. We then want to use our subnet mask, which has 1s where the network and subnet part of the address is, and 0s for the rest. And we'll perform a logical AND operation again, which gives us the following output for the subnet address. To convert these into dotted decimal notation, we need to split them up into 4 bytes or octets of 8 bits each again. These individual bytes can then be converted back into decimal values. And we have our subnet mask and subnet address for this subnet. So now we can complete our table. We have the subnet mask in dotted decimal notation, as well as our subnet address. Just remember that this is only the subnet mask we chose based off the number of subnets we wanted. If we wanted more or fewer subnets, the subnet mask would change, and therefore the subnet address would be different too. Looking back, we can see how many bits we've used for each section. We've used 11 bits to address each subnet, leaving 13 bits remaining to address the hosts within each subnet. This allows us to have up to a total of 2,048 subnets, each with up to 8,192 hosts. I hope that you've been able to follow this simple example of IPv4 addresses using a class-based system. If there are any other topics you would like me to cover, leave a comment down below and I'll see what I can do. Thanks for watching.